last time we continued talking about open-closed sets, and we're pretty much done talking about the main properties of open and closed sets, but there's still a little bit left over. So, for instance, there's this exercise to show that any finite subset of a metric space is closed. So let's prove that. Well, we know that whenever you have a finite union of closed sets, that is closed. So we just need to show that any one-point set is closed. So, um, the proposition we'll prove is that if P is in the metric space E, then the set consisting of just P is closed. Okay, why is this? So if you look at the complement, and you take an element in the complement, so you want to show that there's some neighborhood centered at Q that does not intersect the set P. In other words, such that P doesn't lie in it. Well, then just let R be less than the distance between P and Q. Then the ball of radius R centered at Q does not contain P. P is not an element of this, right? Because if it were, then the distance between P and Q would be less than R. So this set is open, so the set consisting of just P is closed. So any one-point set is closed, and so therefore, since finite unions of closed sets are closed, any finite subset of E is closed. All right? Okay, let's look at another example of a closed set. So let's look at, suppose that P naught is in the metric space E, and R is greater than 0, then the set of elements X and E whose distance between P naught, whose distance to P naught is equal to R is closed. Right, so for instance in R2, if this is P naught and you have some radius R, then we're just looking at the points on the circle. Right, the points on the circle form a closed set. The circle is a closed set. Okay, let's prove that. Well, we know that if you look at the elements X and E such that the distance between P naught and X is less than R, this is open because this is just an open ball, right? So we know that let's see here, open, okay, we know this, and also we know that the set of elements such that the distance between P naught and X is less than or equal to R is closed. And so therefore the complement of this, right, the complement of this set is open. Well, that is precisely the set of elements X and E whose distance to P naught is greater than R. So you know that the elements whose distance to P naught is greater than R is open, and you know that the set of elements whose distance to P naught is less than R is open, so therefore, so the set of elements whose distance to P naught is equal to R is closed, right? Because, just to clarify, because this set is the complement of set of points whose distance to P naught is greater than R, union the set of points whose distance to P naught is less than R. This is open. So the complement is closed. All right, so those are two examples of closed sets. So just using these properties of closed sets being the complement of an open set and so on is useful, right? And the finite union, finite intersection, that kind of thing. All right, let's look at some examples that are neither open nor closed. So for instance, if your metric space is R, and A and B are real numbers with A less than B, then the half open interval, like this, so this consists of all elements x in R such that x is greater than or equal to A but less than B, this is neither open nor closed. Okay, let's prove that. So we have to justify why this is true. So let's say here's A and here's B, and you look at this set. So to be open, every point inside has to have some neighborhood contained in that set. So, well, you see there's one point in this interval such that there is no open neighborhood centered at that point that's also contained in that set. Right, that point is A. So this set is not open because every neighborhood centered in A contains numbers that are less than A. So remember, we're talking about, right, we're looking at E equals R and this subset S, right? And we're claiming that the subset S with the induced metric, this is not an open set, right? If it were open, then it would, if it were open in E, right? It's not open in E. It's not open in E because there is a point, namely A, such that there is no open neighborhood centered at A that is a neighborhood of E that is completely contained in S. Now the set, okay, so that shows why the set is not open. Now let's prove that the set is not closed. Well, in order to be closed, the complement would have to be open. But now what's wrong with, how do we know that the complement is not open? The complement of this set is not open because, so open means that for every point in the set, there's some neighborhood that is contained in the set. So to be not open means that there exists a point, right, such that there is no neighborhood that lies in that set. So in other words, every neighborhood has to not lie in that set. So why is the complement of this interval not open? Because if you look at B, right, B is in the complement, but there is no neighborhood centered at B that lies completely in S complement. There's no interval around B that is a proper subset, that is a subset of S complement, because every neighborhood of B contains elements. I was going to say less than B, but it's not just that it's less than B, right? Contains elements in the interval from A to B. Okay. So this set is neither closed nor open. All right. Now, there are also some things in the book which I will probably skip. Okay, maybe one more example. So let's just look at R2. Let's say A is a real number. And we look at all elements on this half plane. So we look at all elements x1, x2, such that x1 is greater than A. So I claim that this is open. So claim that this set is open. Okay, let's prove that. So we have to take an arbitrary element in this set, say here. So let P, so let's call this set S. Let P equal x1, x2 be an element of S. So we know that x1 is greater than A. Right? So consider, what should our open ball be? We should take the radius to be anything less than x1 minus A. Right? Consider the open ball of center P and radius x1 minus A. That's the biggest radius we can work with. We can always work with a radius that's smaller. All right, so let's show that this open ball is completely contained in S. Well, we have to take an arbitrary element in that ball and show that it is in S. Right, so if Q equals y1, y2 is in this ball, then, well, let's see, what are we trying to show? We want to show that y1 is greater than A, right? That's what you have to do. Now, what do we know about the distance, or the absolute value of x1 minus y1? Well, this is going to be less than or equal to the square root of x1 minus y1 squared plus x2 minus y2 squared. right? That's just a general fact. And this thing on the right is precisely the distance between P and Q. And the distance between P and Q, well, we know that Q is in the ball, so the distance between P and Q has to be less than x1 minus a. All right? So what does that tell you? Well, we know that y1 is equal to x1 minus quantity x1 minus y1. All right? And this is greater than or equal to x1 minus the absolute value of x1 minus y1. Right? Because the absolute value is going to be greater than or equal to x1 minus y1. So when you subtract the absolute value, that is going to be, you're subtracting possibly a greater number. All right, now this, because this, now we use this fact that this is less than or equal to, actually it's strictly less than this, so therefore this quantity here is greater than x1 minus parentheses x1 minus a, which is equal to a. And so therefore we showed that y1 is greater than, so notice the greater than sign here, we get that y1 is greater than a. And therefore, Q is in the set. Q is in the set S. And so therefore, S is open. Okay. One more thing before do we have time for this? It's a bounded set. Since that's a different topic, the concept of a bounded set, we'll talk about that in a different video. Okay, thanks.